Now that we have all of our basic information, let's try to do an actual Hardy-Weinberg equation problem. So we're going to start out with our little population of cats. We've got maybe our feral cats or whatever. So we've got our cats with the tufted ears, 48 of them in our population. We've got 36 with the short tufts and 16 with no tufts at all. Since we already know what the relationship is between genotype and phenotype, we can infer the genotype of all of these cats from their phenotype. So we have 48 big A, 36 big A, little a, and 16 little a. So what we're going to want to do next is we're going to want to relate those numbers to our Hardy-Weinberg frequencies. So let's calculate this out so we can make the relationship. The frequency of big A, which is going to be 48 divided by the total number of cats, which is 0.48 because the total number of cats is 100. So the frequency of big A, little a is 36, also divided by 100. And again, this is going to be 100 because 48 plus 36 plus 16, our total number of cats is just 100. And that makes these numbers easier. It's going to make me have to fudge a number later. So 0.36, that's our frequency of big A, little a's. Our frequency of little a cats, our short tufts or no tufts at all, is just going to be 16 over 100, or 0.16. So now we have our three frequencies, and that tells us if we are in Hardy-Weinberg, if we're in Hardy-Weinberg equilibrium, these frequencies should tell us or should give us back our Hardy-Weinberg numbers, p squared plus 2pq plus q squared. So our frequency of big A should equal p squared, our frequency of big A, little a is 2pq, and our frequency of little a should equal to q squared, if we're in Hardy-Weinberg equilibrium. All right, so that is what we're going to be testing. We're going to be seeing, do these numbers actually match up? So the easiest way to do this is to first calculate P and Q using our homozygote numbers. So we're going to calculate P from the 0.48 number, and we're going to calculate Q from the 0.16 number. So those are our homozygotes. Okay. So we're going to root both sides to get P squared down to P. So we're going to take the root of 0.48. And that's going to tell us that P is just about equal to 0.7. It's not going to be, it's actually going to be like 0.698 something. But we're going to call it 0.7, so I don't have to do real math. So now we're going to do the same thing to figure out what Q is if we're in Hardy-Weinberg. That's everything in white is if we're in Hardy-Weinberg. So Q is going to just be root of 0.16, which is 0.4. And that one's actually equal. So now we can see, do these numbers, will they predict our frequency of our big A, little a individuals? So do they? Well, we can find out 0.7 times 0.4 times 2. Okay, what does that equal? Does it equal a number that we like? And I'm just plugging it into my calculator because I wrote it down, but I never trust myself. So I should have had the calculator up on here. That would be really cute looking. But I'm not that good at screencasting. So this equals to 0.56. So that's pretty far off from what we actually observe. What we actually observe is 0.36. So our observed value is very different from our predicted value. So this is what we expect to see if we had a P of 0.7 and a Q of 0.4, which also don't add up to 1 for some reason because I picked some weird numbers here. So our observed value is not matching our expected value. Our P's and Q's don't add up to 1 because these aren't our actual real allele numbers. And so we're getting, all of our numbers are off. Okay, so our expected does not match our observed, and so that tells us that we are not in Hardy-Weinberg equilibrium. So this is how we do these problems. So we figure out P and Q from our homozygotes, and we look to see if they match our heterozygotes. Sometimes we have to do this in slightly different ways, but as long as you understand what all these numbers mean, then you can fool around with them more.